Hello, IBSL2. Tonight's topic is 7.6, constant velocity and closest distance. Our essential question tonight is how can we apply our knowledge of 2D vectors to real-life problems? We have some definitions to start with. The first one is the constant velocity. Whenever you see those words, you're going to assume there's no change in direction or speed. Also, the problem might not say that, a constant velocity, but if they give you a direction vector, then you're going to assume it's a constant velocity, unless they tell you something different later in the problem. The other things you need to realize, the first part is whenever you see the word due east or west, it's going to be a point on the x-axis, or it could be a point from the point of reference, and the y value will be 0. And due north and south is a point on the y-axis from a point of reference, or from a point of reference, and the x would be 0. So possible example, they might be talking about a vector that's 1, 0 would represent a displacement of 1 kilometers due east. So if they were using the origin as our reference, that would be this red dot here. That would be due east of the origin. And the vector that would represent that is 1, 0. If it said due north, the vector 0, 1 would represent a displacement of 1 kilometers if it's using kilometers, and that would be our purple dot here. So if the origin is a reference point, it would be 1 kilometers due north, and our x would be 0, and our y value would be 1. Let's look at our first problem tonight, and we do have we're going to suppose a vector 1, 0 represents a displacement of 1 kilometers due east, and 0, 1 represents a displacement of 1 kilometers due north. And they are using the origin as the position of the port. The position vector v of a ship is given by, this is our initial position, and here is our direction vector. And t is in time and hours since 6 a.m. Our first question tonight is they want us to find the distance between the ship and the port at 6 a.m. So since they said the time and hours since 6 a.m. would include this entire vector, they're really asking you for the initial position. So time would be 0. And we're going to be using our initial position vector to find the distance. And remember, to find that distance, we're going to be finding the magnitude of that vector, and that would be negative 20, the square root of negative 20 squared plus 32 squared. And that would equal the square root of 400 plus 1024, which would equal the square root of 14, 24, which would simplify it to 37.7 kilometers. And again, we're using 3 significant digits here. To find the speed of the ship, we're going to be using our direction vector. So we're going to find the magnitude of our direction vector, and that would be the square root of 12 squared plus negative 5 squared, which is equal to 144 plus 25, the square root of 144 plus 25, which is the square root of 169, which is 13 kilometers per hour. So that is our speed of our ship. Our last question is ask us to find the time when the ship will be due north of the port. So remember, when it's due north, it's our vector will be due north. We would have to set our x value would have to be 0 if we're going to be due north of the reference point. So we're going to use our parametric equation for x to be set that equal to 0. So our parametric equation of x would be -20 plus 12t, and we're going to set that equal to 0. So once we do that, we just solve for t, and we would have 20 equals 12t, and t would be equal to, there's a factor of 4 in both of these, so it would be 5/3 of an hour, which would be equal to 1 2/3 hour. And then, so that's the time when it's due north. So we have to think about this time from the initial position. So remember, 6 a.m. was our initial position. So 6 a.m. And we're going to add on an hour and then 40 minutes, because 2/3 of an hour would be 40 minutes. So that would be, the time would be 7:40 a.m. So we take the initial position and add on the 1 2/3. Okay, so doing that would find the time when the ship would be due north of the port. Our next problems are talking about closest distance, and there are two kinds of problems that we'll be looking at for finding the closest distance. They'll be between a stationary point and a moving object, and then also between two moving objects. So let's first talking about a closest distance between a stationary point and a moving object. So if we have a ship moving in a direction B, so our direction vector B, here's our ship, it's moving along this direction vector, and they want us to find the closest distance between that it would get to point P on land. Then, as you can kind of see, the closest point would be when it's perpendicular to the land. So the ship is moving along here. The closest distance that this ship would get to land is when it's perpendicular to point P. So what we will do is we will find our vector PR, and we will set the dot product of PR and B and set equal to 0, because when any two vectors are perpendicular, their dot product would be 0. So that is how we're going to be finding our closest distance between a stationary point and a moving object. So let's look at our first example here on closest distance. In our example, we have our ship. It left port A, and it's going in direction of 3-4. It is, they want us to find when it's going to be closest to the port, P, and then it also, before that, and it helps you solve that part because it wants you to show what the position of the ship is in terms of T along this vector, and that helps you find when it's going to be closest to the port. So first we have to find our velocity vector, because we want to find when our parametric equation along here so that we can find PR. So to represent R, we need to find the velocity vector. They told us the speed is 10 kilometers. So we know our speed is 10, and then what we don't know is what our K is. We do know our magnitude of our direction vector, so we can find that, put 3 squared plus 4 squared, and then multiply by K to equal 10. So we can solve for K. 3 squared plus 4 squared is is 25, so the square root of 25 is 5, and k would be equal to 2. Then we can use that to find our velocity vector. Our k times our direction vector would equal our velocity vector, so that would be 6, 8. 2 times 3 is 6, and 2 times 4 is 8. And we said our initial position was the port A, so our initial x value is -8, and our initial y is 3. And notice too that the origin here is 0, 0, so our A is -8, 3, and our P is 10, 2. So to find our parametric equation for x, it'd be the initial position, -8, plus 6 for the velocity vector times t. And our parametric equation for y would be 3 plus 8t. So this could represent r for us. It could represent any point along that vector, but we particularly want to find r. So that will represent xy for my r value. And then again, when we're finding the shortest distance between a stationary point and a moving object, we want to find when they're perpendicular. So we'll set their dot product equal to 0. So our dot product and our times our direction vector equal to 0. Our velocity vector equal to 0. So our dot product in this case of PR, remember, would be r minus p to find that vector. So remember, r is what we said, -8 plus 6t and 3 plus 8t. And our p is 10, 2. So we're going to take our x values of r and subtract 10, for that's the point P, and then our y value of r and subtract 2 for our y value of P to find that vector, and do that vector times the dot product of our velocity vector, and we set that equal to 0 and solve for t. So go ahead and try that and then check back in a minute. And when you found your dot product, you should set equal to 0 and then solve for t, and you should have found that t equals 1 hour. The other problems for tonight, we're talking about two moving objects. And the first thing to realize, if two moving objects would collide, if their time is equal and if their components are equal. So if a problem tells you that they collide, you want to set their components equal to each other and solve for t. If they ask for the shortest distance between two moving objects, then you need to remember your distance formula and how to find a minimum. So our example for car A and car B is asking us to find when the cars are closest. So it gives us our parametric equations for car A and car B, and they want to find the closest distance. So go ahead and plug into your distance formula and then check back with me. So you should have found, I took car A and subtracted car B, x values squared, plus then car A's y values minus car B's y values and squared. So when you simplified, inside here you'd have 6 minus 4t squared plus -1 squared, and the square root of that. Now we're finding distance, and they want us to find a minimum. So remember, anytime we minimize, we're going to take the first derivative and then set equal to 0. So go ahead and pause the video, try to take the first derivative and set equal to 0 and bring it back. So when you took the first derivative, you should use the chain rule, and you should find that time is equal to 1.5. Then you need to plug in that time and find the distance and the position.